Good morning, everyone. Afternoon, sorry, apologies. Good afternoon, everyone. My name is Lucan, and I will be your tutor for the duration of the session. Okay. Just by giving me a thumbs up, can you just let me know if you can hear me? You guys have Teams, and just by means of a thumbs up, just indicate whether you can hear me or not. Well, and Cincinnati and Houston have you guys can hear me. Just not, can you just just give me thumbs up? Can you hear me in the team meeting? Or can you just write in chat whether you can hear me or not? Oh, Miss Gloria, I just wanna ask, can you hear me? With me, or can you guys hear me? Just like giving me a thumbs up. Can you just tell me if you hear me? Especially same goes for that on YouTube. Can you just give me an indication if you can hear me? Or is something like my sound? Can one of you guys just indicate whether you can hear me or not? Just by means of a thumbs up? Okay, thank you. So you can hear me. Let me start. Today we'll be doing linear momentum and collisions. Okay, linear momentum and collisions, and some problems on rotation about a fixed axis. Okay, you have already done this in class and should be able to follow these problems as I do them. Okay, just adjust the screen here. Of course, if you have any problems at any point, please just stop me and then ask me to explain again. If not, I'm going to continue. If you don't interact with me, this is an interactive session, guys, so you might want to interact. If you have any problems, just let me know. If you're stuck anywhere, let me know. Let me start in question 1. Those guys on YouTube, if you can hear me, just let me know. This is linear momentum and rotation about a fixed axis. This is linear momentum and rotation about a fixed axis. Okay, there we have a problem number 1. Okay. Question 1. After a 0.3 kilogram rubber ball is dropped from a height of 0.75 meters, it bounces off a concrete floor and rebounds to a height of 1.5 meters. Okay, so a ball is dropped. Question 1. A ball is dropped, moves down, hits the floor, and then bounces up again. Okay? So a ball is dropped, it hits the floor, and then rebounds to a height of 1.5 meters above the floor. Okay, now the first question asks us to please determine. So we've been given the following. We have the mass of the ball. It's equal to 0.3 kilograms. 0.300 kilograms. We have that it is dropped from its initial height of 1.75 meters, and it rebounds, so it rebounds to a final height of 1.50 meters. Okay. They're asking us to first, number 1, calculate the magnitude and direction of the impulse delivered to the ball by flow. Now, what is impulse? Okay, impulse is nothing but the change in momentum. Okay, now in order to calculate the change in momentum, what is momentum? It is mass times velocity. Now, how do we get the change in mass times velocity? We need the velocity initially and the velocity at the end. Okay, now we know the impulse. We are asked to calculate the impulse, and we know the impulse is the change in momentum. Okay, impulse is the change in momentum, which is otherwise written as mass times velocity final minus the mass times velocity initial. That is the impulse. Okay, so let me just quit there. So the velocity of the ball before it hits the ground. We need to calculate the velocity of the ball before it hits the ground. It'll be its initial velocity. So we want the magnitude and direction of the impulse delivered by the floor. So the velocity just before it hits the ground and the velocity with which it leaves the ground. Okay, so velocity initial is equal to 2gh, where 2 is just a constant, g is the gravitational acceleration of 9.8 meters per second squared, and h the height from which the ball was dropped, and you will get the initial the velocity after the ball has traveled this height, after the ball has been dropped from this height. Okay, now let's plug in everything we know so far. We have 2, we have g 9.8 multiplied by the height it's been dropped from is 1.75. Also, this equation comes from the equation of motion. Okay? And this gives us an answer of negative 5,85 meters per second. So negative 5,85 meters per second. So we are taking downwards as negative and upwards as positive. So we have that upwards is positive and downwards is negative. Okay. So we have the initial velocity. So this is the velocity with which this ball hits the floor. Okay, now let's calculate the velocity with which the ball leaves. Okay, or the final velocity attains, the velocity with which the ball leaves the floor. Okay, the velocity final, meaning for that little instant, okay, that rebound velocity is equal to same formula 2dh, okay, 2 multiplied by 9,8 multiplied by the height it travels, 1.5 meters. When it rebounds, it travels the height of 1.5 meters, and that gives us an answer of 5.42 meters per second. Okay, so we now have an initial velocity and we have a final velocity. Okay? The initial velocity, so now we have, so now we have, so now we have V initial is equal to negative 5,8, I'm looking at it, 5, negative 5,85 meters per second, and the final velocity, or the velocity just after it bounces off from the floor, or just after it rebounds off the floor, is 5, which just calculated to be 5.42 meters per second. Now we have told, or we implied earlier on, or not implied, explained that impulse is equal to the change in momentum, which is equal to mass times velocity final minus velocity initial. Okay? We can take the mass out because it's a constant. Okay, the mass in this case is 0.3 kilograms. So 0.3 kilograms. So that's the mass. The velocity is 5.42 minus 5.85. That, if you do that mathematics, which is just simple, you just ended up adding them, gives you, that's almost a third of 10, so 3,38 kilogram meter per second. So that is the impulse. Okay, of course it is in the positive direction, so it is upwards in the positive direction. So the impulse is 3,38 kilogram meter per second. The next part of the question, part 2, excuse me, that part 2 there. Part 2 asks, estimate the time the ball is in contact with the floor and use this estimate to calculate the average force the floor exerts on the ball. Okay, so you need to estimate the time the floor is in contact with the ball, and then you need to use that time to calculate the average force the floor exerts on the ball. Okay, now from impulse, we know that force times time is also equals to impulse, meaning that force is equal to the rate of change of momentum. So this is the force, average force. Average force is equal to the change in momentum over time. or impulse over time. That is average force, and that is both vectors. Okay. Now they say estimate the time that the ball is in contact with the floor. Now the ball is in contact with the floor for, let's say, about mm, the ball is in that contact, so let's say delta t is equal to 0.05 seconds. So 0.05 seconds. Let's say that estimate that this is the time that the ball is in contact with the floor. Now, this is just an estimate. You have taken 0.03, 0.1. It's an estimate. Now, using this estimate, they are calculating average force. Now, we know that average force is equal to the change in momentum over the change in time. Now we have both the change in momentum, we calculated earlier, it is the impulse over the change in time, which we just said is approximately 0.05 seconds, and the momentum is 3.38 kilogram meters per second, and that is seconds, which gives us a force of approximately 7 times 10 to the 2 newtons, or 700 newtons, and the positive upwards direction, okay? Because the force on the ball is upwards, the ball is rebounding or decelerating upwards. And there we have it. We calculate the impulse to be 3.38, and we calculate the force to be approximately 700 newtons. Okay. Now this estimate for the time that the ball is in contact with the earth, you can also check how long the ball stay in contact on Google, or maybe that was an estimate that I made. Okay. I hope everyone understands. If you have any questions, please let me know before I continue. Now, moving on to question number 2. Question number 2 says, a car of mass m moving at a speed v1. So the car has a mass of m and is moving at a speed v1. It collides and couples with the back of a truck of mass 2m moving initially in the same direction as the car at a lower speed v2. So what is happening here is the following. Okay? So we have a car traveling at some speed v1. It smashes into this truck. Now right in front of this car is a truck, okay, who has a mass of twice of the car, but is traveling slower than the car. Okay? And this car, moving faster than this truck, smashes into the back of the car. Somehow they become entangled, and now this whole car truck system is moving at some new velocity. Okay. Now they're asking us, number one, what is the speed of the two vehicles immediately after the collision? Okay. Now there is no numbers here, there is no digits that you need to work with, only symbols. So you need to know from the law of conservation of momentum, okay, from the law of conservation, the law of conservation of momentum. From the law of conservation of momentum, we have that the momentum initially, the momentum of the car initially plus the momentum of the truck initially is equal to momentum of the car final plus the momentum of the truck final. Okay, the momentum at the beginning is the same the sum of the momentum at the beginning is the same as the momentum at the end. Now, the subscript 1 indicates car, and the subscript 2 indicates truck. Okay, so 1 car, 2 truck. Okay, so we have that momentum is equal to the mass of the car times the velocity of the car initially, plus the mass of the truck times the velocity of the truck initially, equal to the mass of the car times the velocity of the car final, plus the mass times the velocity of the truck final. Okay, so there we have these masses. Okay, now we know that the velocity here, the final velocity v1 final is equal to v2 final, because the truck and the car becomes entangled with each other, meaning these two are now the same, they are moving at the same velocity. Okay? So we can actually take that out. Okay? We can just call it the final velocity. So v final is just equal to, if you take out the velocity here and that one, if they are the same and we take it out, we have that velocity plus the mass of the car. The final momentum is then just equal to the final velocity of the mass of the car and the truck system multiplied by the mass of the truck and the car. Okay, so this is the final momentum. The car and the truck is becoming entangled into each other after the collision, and they are not separated, they are now one unit. So they have a mass of m1 plus m2, where m1 is the mass of the car and m2 is the mass of the truck, and they have the same final velocity. The first section still stays there. The mass of the car, the momentum of the car initially, plus the momentum of the truck, denoted by subscript 2 initially. So we have that. Okay, now we can actually solve. We want the final velocity of the car. We want that. Okay. Now, if we start plugging in the values for, we know that the mass of the car initially is m. The mass of the car is m, and the mass of the truck is 2m. We have that the mass of the car is m times the velocity of the car, the initial velocity of the car, so v1, plus the mass of the truck is 2m times the velocity, which is v2. We can take out m, okay, and we're left with v1 plus 2v2. Okay? So this one is traveling 2 times. The truck is traveling at twice the speed, well, half the speed of the car. The car is traveling at twice the speed of the truck. Okay, so Vf is equal to m plus 2m. Working in symbols is a bit different than working with numbers. Numbers is easy, you just plug in and you play. But working with symbols requires you to keep focus. Okay. Now, we want Vf. So what we're left with is, if we add those two up, we have Vf is equal to 3m on this side. And we have that this is m times v of the truck plus v of the car. So Vf, therefore Vf is equal to Vf is then equal to V1 plus 2V2 over multiplied by m over 3m. Okay, the m's cancel. So what we're left with is that the final velocity equal to 1/3 multiplied by v1 plus 2 v2. So the final velocity is a third of the sum of the two velocities. One third of v1 plus 2 v2. That is the final velocity. Now we want what is the kinetic energy of the car truck system. Remember they glided and they are now entangled in each other. Let's just say the bumper of the car is entangled to the rear bumper of the truck and they are now moving together. Okay, they want a change in the kinetic energy of the car truck system in the collision. Okay, so we have that this Vf a third V1 plus 2 V2 is the final velocity. Okay. So now let's calculate the change in the momentum. The change in the momentum. Let me just, there we go. So the change in the momentum. Change in the kinetic energy. Okay. So number two, part two of this problem, they want now the change in the kinetic energy of the car truck system. Of course, if you have any questions, please let me know before I continue. If you have any questions at all, let me know. The change in the kinetic energy. Now, what is the change in kinetic energy? Change in kinetic energy is the kinetic energy final minus kinetic energy initial. Okay. Now, the kinetic energy final will be half times the mass of the car plus the mass of the truck times the final velocity Vf we just determined squared. That is kinetic energy a half mv squared minus the initial velocity, the initial kinetic energy, which is a half m, as that's the car times the car v1, the velocity of the car initially squared, subtract from that as well as a half the truck, I'll just say t there, the velocity of the truck initially squared. Okay, mt vt, that is for truck. So now a half times what was the initial mass of the car? It's m plus the initial mass of the truck. It's 2m. The final velocity we determined it to be now to be v1 plus 2v2 over 3. We determined it early on. That's cubed minus a half the mass of the car m. The initial velocity is just v1 squared minus a half, subtract that as well, these two should actually be, you subtract from that the initial initial kinetic energy. That's the initial kinetic energy of the car and the truck, and this is the car truck system. Okay, so that's a half times the mass of the truck is 2m times its velocity is v2 squared. Keeping up with the symbols. If you were to do some algebra on all of that, it gives you the following 6. M is in all of them, so it can come out as a constant. That's v1 squared plus 4v2 squared plus 4v1 times v2. If you were to multiply all out, 3 times v1 minus 6 v2 squared. Okay. So there you have that whole thing. If you were to multiply that out, put a square there and put a square there. That's what you would get. Okay. Continuing, if we continue to take out the constants, we are left with v4 1 times v2 minus 2v1 squared minus 2v2 squared. If you even simplify that even further, that negative 3 minus negative 3v1. Okay, I got something. Let me just ask, is there a question? Okay. Yeah, I forgot the square there. That's v1 minus 3v1, that's negative 2. That's 4v2 minus 6, that's negative 2. Okay, so continuing our algebra, we have that we can take out from all of them a 2. So 2 will go in there. You take out from all of them a 2, you simplify it further, you get m over 3 because 2 goes into 6 3 times, and then you're left with 2 v1 v2 minus v1 2 minus v2 squared. Now, here's the nice thing about this particular problem. Okay, if you were to go back to your grade 10, or is it grade 11? Yes, you would find that this whole section here can be written as v1 minus v2 and that whole thing squared. Did I forget a... Just check something. Just take the negative out. Alright, let me just check here. I'm just checking if I made an error with the sign here. That's fine. Should be fine. And that, ladies and gentlemen, is the change in kinetic energy of the car truck system in the collision. That's going to be positive. That's also going to be positive. That one's going to be negative. Okay, then we multiply the negative in. Yes, this drops up. Okay. Going to question number 3. If you have any questions regarding that particular problem, please let me know. Otherwise, I will be moving to question number 3. And this question says, and I'm going to draw the situation. The question says, given that we have two blocks that are free to slide along the frictionless wooden track shown in the figure. Okay, now I'm going to draw this track we have, or supposed to have. This is the track. So that's the track. See that. Well, let me try and make a better drawing. It's supposed to curve nicely. Okay. That one looks better. This one looks better. Okay. Okay, so there we have the curve. Not a very good drawing, I'm afraid, but it'll have to illustrate for illustrative purposes. So we have two blocks. This is the first block, block number one, sets up there. Then we have another block here. This is M2, this is M1. And they say the two blocks are free to slide along frictionless wood track as shown in the figure. Okay. Now M1 is equal to 5 kilograms. Just gonna write 5 kilograms, while the height here from M2, they say the height H, this height here between the top of the ring and the flat side of this block H is equal to 5 meters. So the height is equal to 5 meters. So the block of mass M1 is released from the position shown at height 5 meters above the flat part of the track. This is the flat part of the track here. Okay. This block is initially here, it then travels down, and lands here. Okay. Now protruding from its front end is the north pole of a strong magnet, which repels the north pole of an identical magnet embedded in the back end of the block of mass M2, which is equal to 10 kilograms. So this block is released, it slides down. This one has a north pole of a strong magnet, and this one is the north pole of a strong magnet on its backside. That on the front side, meaning they will repel each other. The two blocks never touch. Calculate the maximum height which M1 rises after the elliptic collision. Remember, this one is stationary, so it's going to slide down. The magnetic fields are going to repel each other, and the one block is going to block M1 is going to slide back up it. Okay? So they're asking us calculate the maximum height to which M1 rise after the elliptic collision. So it's going to slide down, bounce against M2 and slide up again. Okay, the bouncing is going to be caused by not a physical contact, but by the opposing magnetic fields. Now, first find the velocity of the block just before the collision. Okay, now let's say number one. First, find the velocity of the block. First, find the velocity of the block. First find the velocity of block M1 for the collision. So just before the collision, we have a formula where we can use this. Okay, is this formula? It says velocity is equal to the square root of 2 times the gravitational acceleration times the height. We used before in previous problems. Now we have the formula for velocity. Now we have that 2 times 9,8, and we have height at 5. So it's 9,8 times 5. That's 9,9 meters per second. So the block is this block. M1 is M2 with a velocity of 9,9 meters per second. Now we have the momentum, or we have the velocity of M1. Now apply the law. Applying the law of conservation of energy. Not conservation of energy, conservation of momentum. Now apply the law of conservation of momentum gives. So if we apply the law of conservation of momentum, we have the momentum of block 1, momentum of block 1 initially, so the momentum of block 1 initially, plus the momentum of block 2 initially is equal to the momentum of block 1 finally plus the momentum of block 2 finally. Because the momentum is conserved in the elliptical collision. So they're applying the law of conservation of momentum, then applying the law of conservation energy. This is an elastic collision. The law of conservation of energy. The law of conservation of energy gives half times m1 v1 squared initially, the initial kinetic energy, plus the of the block m1, and this is the initial kinetic energy of block 2, equal to the final kinetic energy of block 1 the final kinetic plus half m2 v2 squared final. So I hope you track that. So now we have two equations, okay? One for the law of conservation of momentum and one for the law of conservation of kinetic energy. So we have two equations. We have that the speed of M1, so the speed of this block, so the speed of this block here, 9,9 meters per second, just worked it out. Okay? So the speed just before M1 hits M2, we calculated that. Now, let's calculate number 3, the speed. Remember, I'm doing it stepwise. That's why I have 1, 2, and 3 here. There is no show 1, 2, and 3 in the question. I'm just putting it stepwise. Okay. Now the speed. Remember, they just bounce. Sorry. M1 just be bound off block M2. Now the speed of M1 just after collision, so just after the collision, speed of M1 just after the collision. So the speed of one just after the collision, so V1, but final. So the speed of block M1 final is equal to M1 minus M2 over M1 plus M2. If you were to go and work this out, multiply this fraction multiplied by the velocity initially of M1. That formula you can go and work out for yourself, but if you use the formula, anyway, it is just one of these equations here. The equations that I just got. I just solved it for V1 final. It is the equation for conservation of momentum. This is going to be equal to negative a third. This all comes to negative a third times the velocity that we calculate as 9.9, which gives us negative 3.30 meters per second. So we have the final velocity of block M1 is not the final velocity, the velocity just after the collision is negative 3.30 meters per second. Now we have initial velocity and the final velocity per se. Okay. There you go. So now this block M1 bounces off block M2 and starts sliding back up the incline. This incline that I drew originally, this incline. This one. So it slides back up, it bounces off, then it slides back up. Now we want the maximum height that slides back up. Okay, now the maximum height is going to be the mass of the block times G times H max, that is what we want, is equal to a half M1 V1 squared final. That is because it can only have the potential energy. If we solve H max, remember when it slides back up, it has no more kinetic energy. Initial energy is going to be the final kinetic energy, and the potential energy. Those two subtracted from each other should be equal to 0. Because the change in kinetic energy should be 0. Kinetic energy is, well, not the kinetic energy. Energy is conserved, the mechanical energy. Okay. The mechanical energy is conserved, meaning that the sum of the potential energies, well, the sum of the energy at the beginning should equal the sum of energy at the end. Now, originally, or in this case, the potential energy plus the kinetic energy should be 0. That means the potential energy finally is going to equal the kinetic energy originally, because of this problem of this here right here, because all of its kinetic energy is being converted to potential energy when it slides back. Okay? Once it stops at its highest point, it purely has, it is not moving, so it has only potential energy. Okay? All the potential energy was converted from all of its original, its final kinetic energy. That makes sense. This is then equal to V1 with 2G times -3, comma 3 is 0 over the m's cancel. The m's will cancel, of course. That leaves us with v1 a half v1 squared. It's still squared. So that's squared over 1 over 2 times 9,8 meters per second squared. That leaves us with an answer of, that squared is about 9 divided by 1,8, and the half of that, and that's about 0.5. If you work it out, it's about 0.56 meters. That slides back up. So that slides back up very far. That's about, yeah, half a meter up. And what we should work on is like 6 meters, okay? And that, ladies and gentlemen, is the beauty of physics, okay? Or I should say the beauty of mechanics, okay? Newton's wonderful laws of mechanics. Question number 4. Let's look at question number 4. Okay, question number 4. Question 4, we have that, my notes, so this question 4, I'm gonna read it there. A wheel starts from rest. Is it showing there on your screen? Yes. A wheel starts from rest and rotates with constant angular acceleration to reach an angular speed of 12 radians per second in 30 seconds. Okay, so we have this wheel, it starts from rest and it starts rotating with an angular acceleration to reach an angular speed of 12 radians per second in a time frame of 3 seconds. Now, number 1, the first part of this question asks, find the magnitude of the angular acceleration of the wheel. Now, angular acceleration can be calculated if we have the initial the angular speed. The initial angular speed is equal to, well, the final angular speed is equal to the initial angular speed plus the angular acceleration times time. This is one of those equations for angular rotation. Okay, you have seen all before. Now the final angular speed is 12 radians per second. The initial, it starts from rest, so that's 0. We have that angular acceleration, which is what we want, and we have a time of 3 seconds. Now if we were to solve this, 0 goes over, that's 12 divided by 3, so angular acceleration is 4 radians per second squared. That is the angular acceleration. Okay, now part number 2 of this question says the angle in radius through which it rotates in this time. So we need to calculate the angle in radians, okay, otherwise known as that distance. Okay, so the angle in radians. So the final angular velocity or angular speed is equal to initial angular speed squared plus 2 times the angular acceleration times the change in the angle. Okay, so we have that the final angular acceleration is 12, and then you square the initial is 0, square that plus 2, the angular acceleration is 4, we have delta theta. Okay, if we work out delta theta, that comes over, that's 144, that's just 2 times 4, which is just 8, just 8 times delta t. Therefore, delta theta is equal to 144 divided by 8. 144 divided by 8 equal to, this is in radians, 18 radians. So it goes to an angle of 18 radians. That is question number 4. Question number 5 is a nice one. Let's see question number 5. If you want a break, you can take a break. If you have any trouble with any of the problems we've done so far, just let me know. Raise your hand or type it in the question. So assume that no one has any questions. Question number 5. Question 5. Question number 5. Let's see. A wheel 2 meters in diameter. So we have a wheel 2 meters in diameter lies in a vertical plane and it rotates about its central axis with a constant angular acceleration. Okay, so we have that this wheel has an angular acceleration of 4 radians per second squared. So we have that angular acceleration of 4 radians per second squared. This is wheel. The wheel starts at rest at t equals 0 and the radius vector of a certain point P on the rim makes an angle of 57 degrees. So theta is equal to 57.3 degrees. With the horizontal at this time. Now at 2 seconds, now find the angular speed of the wheel, and for the point P, the tangential speed, 3, the total acceleration, and 4, the angular position. Now, number 1, we need to find, number 1, the angular speed of the wheel. So we know that angular speed, V final, angular speed is equal to the initial angular speed plus the angular acceleration times time. Now we need to find it for 2 seconds. Okay, after 2 seconds. Now the initial speed is 0. It starts from, the wheel starts at rest t0. So plus the angular acceleration is 4 radians per second squared times the time 2 seconds, which gives us the final angular speed of 8 radians per second. So we have an angular speed of 8 radians per second, 8 rad per second. Now, number 2, the question asks us to please find the tangential speed. Okay, now tangential speed meaning just the linear speed. So we have the angular speed times the radius, that is the linear speed. Tangential speed is also known as the linear speed. And that is just the angular acceleration, the angular velocity, the angular speed multiplied by the radius. Now, angular speed is just, it was calculated to be 8, after 2 seconds, 8 radius per second. And the radius is 1 meter. So 8 meters per second is the tangential speed or the linear speed. Okay. Number 3, they ask us the total acceleration. So the total acceleration. The total acceleration. Now the total acceleration, is equal to the square root of the tangential acceleration plus squared plus the radial acceleration squared. Okay. Now at, the tangential acceleration at, the tangential acceleration, is equal to the angular acceleration times the radius. The angular acceleration times the radius. So that's the tangential acceleration. That is, angular acceleration is 4 radius per second squared times the radius of 1 meter. That gives us 4 meters per second squared. So that is the tangential acceleration. Now, the radial acceleration, on the other hand, radial acceleration is equal to the tangential, the angular speed times the radius, the angular speed squared times the radius. Now, the angular speed after 2 seconds is 8 radians per second. So square that times the radius of 1 meter, you have that it's 64 meters per second. The angular, the radial acceleration. Now, the total would be the square root of 4 plus the square root of 6 and finding the square root of that, the square of 4. So basically, the total acceleration is then equal to square root of a, the tangential acceleration squared, which is 4 squared, plus the radial acceleration squared, which is 64. Sorry, that's 64. 64 squared, and the square root of that sum gives us 16 plus, I have no idea. Let me just find the sum of that whole thing. Is 4112 gives us, the square root of that gives us close to 64.1 meter per second squared. 64.1 meters per second squared. That is apparently the total acceleration. Okay, so we found that the angular speed is 8 rads per second. We find that the linear speed is 8 meters per second. We found that 64.1 meters per second is the total acceleration. We just need to find the angular position. Okay, number 4, the angular position. Okay, how do we calculate angular position?